have a proton. All right. Got it. So I have Dr. Ovani Singh from Technical University of Munich. And he graduated from same university in 2023. So now he's a postdoc. So I think it's sort of half theory, half experiment, or half experiment, half theory, strong interaction, final state interactions. So that's why he's on his way back to Munich. So he will explore strong interactions in three-hadron systems, LHCs. Please.
Thank you, Stu, for inviting me. And yeah, so giving me the opportunity to talk about recent results from Alice on strong interaction in three-hadron systems. So this will be talked particularly about the three-hadron systems, and we will be looking into the strong interaction, maybe quite different from the usual way. So yeah, let me start with the famous plot of running coupling constant of QCD and the function of momentum transfer. So I mean, I just wanted to highlight here two regions. In the one, like asymptotic freedom, where the quarks and gluons are kind of free or quasi-free, and can be using various techniques. Let's say we can go to the heavy ion collisions and to the properties of quark and gluon from QGP. The other hand, if you go towards small momentum transfer, the alpha else becomes large, and at some point of time, the theory becomes non-perturbative. And then the idea is how do we study the dynamics of quarks and gluons, and one way to go into the details in this plot to not look at the quarks and gluons, but rather look into the confined objects, which are hadrons. And here one can deploy, for example, effective field theories, where the degrees of freedoms are hadrons and, let's say, mesons and baryons. Now, this approach actually needs one cost to be paid, is that you have low energy constant, and those low energy constants need to be tuned to this some sort of hadronic interaction data. So we need, in a sense, experimental data to tune the low energy constant of the theory, and then access the sort of dynamics and study these kind of properties of QCD. Now the question comes, how do we really perform the experiment, and what are the hadronic interactions? Whether we just look at the two-body cases, or we have pictures beyond two-body, for example, three-body interaction and many more. So it already turned out that if you consider the simplest system, which is AD, nucleon-deuteron scattering, the role of the three-body forces becomes important here. So what I show here on the, it's a right-hand side plot, which is the elastic scattering of nucleon and deuteron, differential cross-section as a function of scattering angle. So what we see here is in the low scattering angle, the data can very well be described if you consider the calculations where there is only two-body nucleon-nucleon interaction. But it turns out that if you go towards a larger scattering angle, there's a deviation between measurement and the data, prediction. So then you need, for example, the obvious way to go further would be to look into the many-body picture and then include three-body forces here, which is the nucleon-nucleon-nucleon. And the red band here is computed using 2 + 3-body force. So, and now we can see that at least for some of the energies, that the agreement between the prediction and the measurement is better. So this was one of the examples. Now we can go to much more, let's say, many binding energies from the nuclear spectroscopy. And here you have now binding energy, let's say, for many light nuclei up to beryllium. So focusing on one of the examples here is the helium-4. The measurement is shown here in the green band, and then the binding energy computed only considering two-body potential in blue. So as you can see that there is a prediction of the binding energy, the nuclei are predicted to be underbound if you use only two-body forces. And including the three-body force in the calculation brings the prediction close to the measurement. So we have another example to look into and then say that, okay, we need interactions beyond two-body. The third example that I want to give is not just the normal nuclear densities, but also if you go towards the higher densities, for example, neutron stars, where the nuclear density becomes like approximately 3 times the normal nuclear density. And here, from the theory, already if you look, if you go into the picture, the baryochemical potential becomes sufficiently, let's say, favorable enough to have new degrees of freedom, for example, hadrons. And now not only just the nucleon interaction in the complex system like neutron star, but also you have now hadrons which could play a role. And we want to now say, if we want to really provide a description of such a complex object, we want to have not only just two body forces under control, but we also need to have dynamics where the three body force also play a role, and we need to control, put like a constraint on this. So the traditional way to study the force in hadron-hadron interaction is to look into scattering. For example, you have nucleons, nucleon scattering, and there are plenty of data available for the, like say, neutron scattering from classical approach. There are also three nucleon interactions which you can, I show you the example already that you can look at it, is the nucleon-deuteron scattering, and there are available data which we can put. But as soon as we go to the, from the normal nucleon case to hypernucleon or nucleon hadron case, the data becomes scarce or almost not available at all. So we need new methods or ways to study interaction in the complex systems, including strain and charm sector. So one of the ways would be to go directly to the collider experiments. For instance, we have LHC experiment where we can have proton-proton collision, and here in this case we can have a bunch of particles are like not only just the normal neutrons and protons are produced, but also hadrons and let's say strain and charm sector. And now we can choose a particle pair of our interest and then study interaction. So the way we do is use the femtoscopy tool and Alice detector. So in Alice we can really find out particle, like perform a PID of a particle with a very low momentum. So it's possible to identify a particle with smaller momentum. And there we can then perform sort of a correlation analysis in the relative momentum of the particle pairs. So the relative momentum for this talk, I always call it K star in the pair rest frame. So the observable I'm talking about is correlation, and experimentally what we look at is number of particle pairs produced in the same event, so where these particles can actually interact for a given K star, divided by the number of particle pairs where the particles come from different events, so they don't interact. And this is done just to account for the phase space. Theoretically, this definition is given in a bit more sophisticated way, where it's called Cumulant formula, and there are two terms. The first term here is related to the production, and it says, we call it source, where the particles are produced, and it is basically a probability distribution for a pair of a particle produced at distance r star. And the second term here is then, because the particles, when they pop out from the collision, they can also interact, and this is taken into account by using the relative wave function. And now the observable is normalized such that at large K star, when the particles are far away from each other, they won't interact. So the correlation function becomes one unity. So now, for instance, if you look at the attractive interactions, which is like, for example, this one here in the green curve, so this will give you a correlation function goes above unity. And for example, if you have repulsive interaction, then the pairs tend to go away from each other, and therefore the correlation function go below unity. So with this exercise here, we really see that the femtoscopy method can be used to study interaction only if we have a source under control. So we can perform a measurement, and if this guy is under control, we can study the interaction for the particle pairs. So Alice in previous years did enormous efforts to really put the source under control. And the idea here is in proton-proton collisions, when the particles are produced, we assume that there's a primordial distribution of the particle pairs for given distances. And there, all these particles are basically coming from the interaction point for a given, and then you just model the distances as a distribution, which is typically a Gaussian distribution with width R4. So this is what we call R4. And then we also know that this distribution should get affected from the strongly decaying resonances. So for example, if you have delta resonance, which will decay into a proton, and so it will effectively increase the source size here. So this we put into account by using simulations and thermal phase model. So the yield of the resonances are under control, and also the kinematics of the daughter particle can be accounted using some simulations. So this part is under control. So what remains not kind of not under control is the R core. And this can be done now performing measurement of particle pairs where interaction is well known. So for example, if you look at now the distribution, here I show is the R core, which is the width of the Gaussian distribution, as a function of transverse mass of the particle pairs. And the transverse mass in our case is computed using average transverse momentum, KT, and average mass of the particle. So now each point here is a measurement of the correlation function fitted with the calculation and then extracted R core. For instance, if we now look into the red points here, they are performed using a measurement of pion correlation function, considering only Coulomb interaction, and then quantum statistics, because you have pions which are bosons, and you need to really account for this quantum statistical effects. So once they are done, you can fit the correlation function and then extract R core. And this is done for several different transverse mass regions, and then we see that there is a nice empty scaling obtained for the pions. Similarly, the other case is kaon meson interaction. So now we have, kaon proton interaction, and here now we have measurement in the gray band, and then the red band is the calculation computed using chiral potentials. So the interaction is under control, and then we have extracted R core as a function of transverse mass. It also lies on top of the pion data points. And the third one here is then the baryon case, which is proton-proton correlation function, considering Coulomb interaction and argon V18 for the strong interaction. So what we see here in the measurement, so there's a peak-like structure, and then we fit the correlation function with the model, and then extract R core. And here you can see that these data points actually lies again in the similar manner on the same empty scaling band. So with this, we can conclude that for all hadron-hadron pairs in proton-proton collisions, there is a common empty scaling, and which can be used now for those particle pairs where the interaction is not known. So only thing that we need to really know is from the analysis, we can fix the transverse mass pairs, transverse mass of the particle pairs, and then extract R core for a given particle pair of our interest.
Is the R core the width of the Fourier transform? How is your R core defined?
Sorry, I think I need to go back. Here, it's a width of the Gaussian distribution in the calculation. So you have
Yeah.
So because not all particle pairs can participate in the final state. You wouldn't really see the final state interaction because they can be really far away from each other. So this is done using a PDF, let's say the probability distribution, which is a Gaussian distribution, and then it is associated with the some sort of production mechanism, because you have now all the particles distribution can be assumed to be a Gaussian distribution in proton-proton.
And then you fit the
exactly
momentum.
Yeah, so we just do in the momentum space correlation function and extract R core. So
what are these two outlier points in a small MT?
Exactly. I didn't point out, but I was expecting a question here. Thank you. So these as you can see that there is a nice trend of the empty scaling, but at very small empty transverse mass region, there is a breakdown of this scaling. And this is not understood from the experimental point of view, but from a hydrodynamics, people are trying to understand whether there can be further explanation. So at the moment, what we know is the scaling holds up to smallest transverse mass up to 0.7 GeV, but then there's a certain.
So this is pi plus, or what system is that? Where you have
pi plus, yes. Could also be that you have different production mechanism at really short distances.
Is the last 2 point only pi plus, or is
only for pions, because you cannot reach to the smaller transverse mass because you have constraints on the mass of the particle pairs. So you cannot do that. But for pions, it is possible to reduce, really go down to the smaller values.
MT. Okay.
Exactly.
The pointer on one also deviates from the scaling, right?
Which one? Oh, this one here?
Yeah.
This could be also part of systematics, because you have rather large. So what we see here is large width, right? And also we have different baselines. So there is a possible systematic, but what we really constrain, if you look into the all points here, they are more or less in the same ballpark.
So what's a pair of this low pion, the outliers that's Raja?
Yeah, this is only for pion case. Pi plus, and pi minus pair. Yeah. And in this case, we have considered two different, because sometimes the background is not under control. So we kind of trying to model the background using a polynomial. The background here would be all those particle pairs which would not come from the final state interaction, but they are like possibly from like weak decays or material contribution. Right. So we have now a way to constrain our core, and obviously, if you pick up a particle pairs, for example, hadrons, they could also come from a resonance decays, and one need to really account the effect of short-lived resonance, which would feed into your particle pair of interest. This can be done using simulation. So all what I was talking about is the source, and it's under control right now. And with the help of this study now, it was possible to really explore interaction in many hadron-hadron pairs in the past years, and two-body femtoscopy has been successful to not only look into baryon-baryon interactions, but also baryon with strangeness and also some charm sector. And we have been really able to publish many results in the past years, and now the question is whether we should just stop here two-body case, or we really need to go and we can use this technique for the three-body sector as well. And it turns out that, yeah, I mean, we can do it because you have another particle which we can substitute with a deuteron. And now the question becomes whether deuteron should follow the same empty scaling as it was shown for the hadron-hadron pairs. And so we can assume that, okay, the deuteron also follow the same empty scaling, and we can fix the source size. And it turns out that for the kaon deuteron case, it is around 1.4 fermi. So this is fixed from the empty scaling of hadron-hadron pairs, assuming that deuteron also follow the same empty scaling. And now looking at the measurement on the right-hand side, in proton-proton collisions at using high multiplicity events, we can see that as a function of k star, the correlation function, large k star, there is a flat behavior, meaning that there is no interaction. But if you go towards low k star, there is a drop which tells us that there is an overall repulsive interaction in the system. Now, assuming only Coulomb interaction, as shown here in the green line, we cannot really reproduce, we cannot describe the data, which means that we need inclusion of a strong interaction, and one can use it, one can perform a simple business here. So use that deuteron and proton both are point-like particles, assume an LHC Debauchet model, and then strong interaction appears here in this calculation via the scattering lengths. So the scattering lengths for a K plus D system was computed in two different manners. The first one was to look at the KD scattering data, the cross-section data, and fit them, and then extract our A0, which is the scattering length, which turned out to be around 0.5 with a negative sign indicating that there is a repulsive interaction. The other one was fixed center approximation calculation. So you have KN interaction, you can perform a fixed center calculation, and then effectively the scattering length turned out to be in the similar ballpark. So with these two values and Ladensky-Debauchet model, the calculated correlation functions, now we can see here on two different shades of the blue color, they tell us that there's a nice agreement obtained for the given source size, which is about 1.4. So from this slide, what we learn is that deuterons actually follow the same empty scaling because we started with an assumption, and this is now a validation. Also, the calculated scattering lengths, which were somehow related to this KD scattering measurement, are cross-verified with the measurement. So we see that.
So the scattering lengths and effective range are fitted or calculated? So
they are calculated fitting. In the first case, we just fitted to the KD scattering data. So the effective range of expansion formula we use, plug it to the.
But it's fitted then to your data, right?
No, not with this data. This KD scattering data. I mean the traditional deuteron kaon scattering.
Oh, there's deuteron scattering data out there. Okay,
yeah. Okay. Sorry, I was not clear enough. Yeah, thank you for the clarification. Yeah, so now this is a validation, right? And we also see that this works for the deuteron case. So now let's go and use the same system, but change one of the particle, which is now, instead of a kaon, look into a slightly complicated model, which is PD. The measurement tells us that, again, there is a flat behavior here, and then in the low K star, we can see that there is a depletion, indicates that there is a repulsive interaction in the system. The source size, now we see that deuterons follow the same empty scaling, and it turns out to be, for this particular analysis, it is about 1 Fermi. So we are really dealing with the short distances, because, in this
so what is the MT of a proton deuteron system? I mean, I can see this what the MT of a kaon when you have the same particles, but now you have two.
Yeah, so the MT actually becomes a little bit large.
So how is it calculated? The average, or is it the mass center of mass, or what is it?
We look at the average values. We always look at the average MT of the particle pair. It is about 1.64 Fermi as GeV over C squared.
Well,
yeah.
Okay.
I have this slide in the back of my could
So
also.
the size is actually smaller than the kaon deuteron.
Yes, because you go to the larger empty scaling. If I go back to this plot here, so you have so you go to the larger and larger empty, you tend to go towards the smaller and smaller distances. So the PD case, because the particles are heavier, so you will have the average empty will be larger from the analysis, and that's how you go to the larger.
Is that because of your coverage is larger, or is it?
So both cases, yeah. I mean, I would get.
But you can. But then
the first case is
measurement. You have to do some kind of extrapolation to the behavior at large MT, right?
No, this is fixed from the analysis, right? So you have the mass, which is already computed. So you have mass, which is
I know,
but the momentum spectra actually.
You are saying the fact that the kaon deuterons and proton deuteron size are different now.
Yes, that's true.
And that's because
you have different momenta of the kaons and protons. Also, the mass is different. So you will have for the proton, the mass is almost twice the kaon mass. So it will slightly shift towards larger empties, right? And then the source size will become smaller. Of course, there is also a role of strongly decaying.
That's purely kinematic effect. I thought you can. Do you think you should actually correct for the kinematic effect, get the true size of correlation function?
No, that's what we get here, right? It's the effect of kinematics, right? So you have a scaling, which is because you have a scaling, like not in proton. I cannot even call about a flow, but there's a common behavior of the particle moving out, and this is solely associated with the PT, which is the momentum, transverse momentum of the particles. So there is an effect of kinematics, of course. On top, which I did not mention, for kaons, the strongly decaying resonances are different. So there will be different attribute of the effect of the strongly decaying resonances with respect to the proton. I mean, deuteron, we do not really consider any. There is no.
Okay, go ahead. I'm going to come back to this.
Thank you. Right. So I was here. Good. So we have now the measurement, and considering only Coulomb interaction with this source size, we can see. I mean, there is kind of qualitative description, but we also know from the scattering experiment that the PD system has strong interaction in there. So you cannot just be satisfied with the Coulomb. So the next obvious question is to use Coulomb plus strong interaction. And here again, I use assuming that the deuteron and proton are point-like particles, use the Lambda-Debouchet model, and then compute the correlation functions for different scattering lengths from previous scattering measurements. And we can see that, okay, I mean, here there's a drastic difference between the measurement and the calculation, which indicates that, of course, if you have complicated system like proton and deuteron, there's a Pauli blocking at place because you have two protons which are identical in a sense, and therefore such simplification of the calculations like effective two-body calculations do not work. Also, in the effective two-body, mostly we deal with the asymptotic form of the interaction, where we are now at very short distances, and therefore we need to really deal the dynamics of the three nucleon in a proper three-body way. So the obvious way now is to really compute the correlation function, treating the proton, neutron, and proton as a three-body, and not the effective two-body. So to do that, during my PhD from Uni Group, we collaborated with the theories from INF and PISA and NC State University to come up with an observable. Again, it's a correlation function, but now the things change. So the things change in a way that you have now a wave function, which is three-body wave function. So at short distances, they are not deuteron and proton, but three nucleons asymptotically go to a PD state. And this is a three-body wave function which we can compute using hyperspherical harmonics and different interaction potentials. The second term here is now the source term, which is now not only like we do not look at the PD source, but we look at the nucleon source, which basically come out, and the RM here is the source size for the two nucleon pairs, which will participate in PD system. The third term here is because we know now that deuteron is a light nuclei, and it has to form at some point of time the three nucleon that pop out from the collision. Two of them will have to form a deuteron, and in order to account for that, we use this AD, which is in a sense a deuteron formation probability. So we can compute now all of these in gradient and then compare with the data. So let's look at the calculation which is compared with the data. First of all, now the scale is different, so I want to really put an emphasis that in the data itself, there is a structure here, which is a dip-like structure, indicating that there is some sort of signal apart from the drop. And now if you look at only Coulomb prediction, calculated for the, also treating the anti-symmetrization with respect to the proton inside there, we can see that the Coulomb only calculation is not able to describe the data. As we can see in the lower panel, the n sigma deviate with respect to, up to like 5. And then the second case is now, because you also know from the scattering data, we need to plug in the strong interaction. And easier way to use is the argon V18 potential. This has been already used for the proton-proton correlation function. And we are, it provides really a good description of the proton-proton correlation function. So argon V18 potential, and for when the 3 nucleons are close in phase space, we use the 3-body Urbana-9 potential for the genuine 3-body forces. Considering only S-wave interaction, we can see that with respect to Coulomb, there is a more repulsion. Also, we do not see this kind of description of the dip-like structure here. Then, including more partial waves, so going from S-wave to now D waves, including P and D wave, the attraction in the P and D wave pushed the correlation function above Coulomb, and then it provides a very good description of the data, not only just the drop, but also the dip. And as we can see, the n sigma remains close to 1 for all K-star range. So this was done using phenomenological potentials like argon V18 and Urbana-9. To validate this calculation further, we use another way, which is spineless effective field theory at the next to leading order. And this, I wanted to just put an emphasis that this theory is now more close to the QCD Lagrangian, because you directly employ the symmetries from there, and then compute the correlation function in the region where the theory is valid. We can see that there's a very good description of the correlation measurement using spineless effective field theory. I'm sorry. All right, so we have now from these two exercises and the measurement, what we learned that the deuteron and proton system cannot be treated as effective 2-body at shorter distances. Additionally, such measurements are sensitive to higher order partial waves. And we need to treat the, when we compute the correlation function, we need to take care of those higher order partial wave contributions. So I talked about the 3-body interaction in general, but I did not really focus on genuine 3-body force when you have 3 nucleons closing. So this can be, in a sense, understood by looking at calculations without Urbana-9 potential. So here I show you a plot. So we have the correlation function calculated with argon V18 potential for 2-body case and Urbana for the 3-body case, divided by without Urbana calculations, just to see the effect as a function of K star. So here, for the source size around 1.4 for me, we can see that the effect is about like 2 to 3%. But I mean, if you look at the errors of the measurement, at the moment we cannot really distinguish these two scenarios. But when we look for run 3, and the analysis is already in place, we are looking at, and the preliminary estimate of the calculation, measurement tells us that there is a 2 orders of magnitude increase in the statistics. And with that, we will be able to really pin down, we will be able to have the errors within 1%, and that will really be helpful to pin down the contribution of the 3-body forces. Not only just that, because we have such a large increase in the statistics, we can also put a kinematic constraint on the particle selection to select the particles from large transverse mass region, which will effectively means that you go to the smaller and smaller distances, and then the effect of the 3-body force becomes even large. So it will be possible now to also look at the different densities, because when you go to the shorter distances, it is basically mimicking the large density environment. So this exercise will also allow us to perform a measurement of the system in an effective density dependent environment. So from both KD and PD analysis, from run 2, what we understand that these kind of measurements actually are helpful to understand the interaction in 3-body system, and also place an avenue to study interaction not only just for normal hadron deuteron, where you have proton and kaon, but also include strangeness, for example, lambda neutron. Then this can be done.
So the 3-body,
yes,
it's like enhance the correlation.
Yes, it's an attractive type of. So here you see the increase, and here you see the decrease. It depends. It's a kinematical. Yeah. So
data is a depletion. But,
yeah.
So then where do we see the data?
So the data. This depletion has nothing to do with the 3-body force. It is mainly coming from the inclusion of partial waves. So if you look into the interaction, the role of the 3-body in these kind of systems, the higher order partial waves, which we normally neglect, we just deal with this S wave and we say, okay, this is the contribution. But we have also like P and D waves, this actually brings down the correlation function in deep over here.
But it also does a huge way. The S wave only is blue, right?
Yes, it's just this
so it has a huge effect on going to the higher partial waves.
Yeah.
Exactly. This is the beauty, because two of the particles now can be in S wave. Third one is because you sum up the angular momenta, and third one can be either in S wave or in the L wave, like L equal to 1 or L equal to 2. But the S wave itself for the two-body system is attractive, and it's a huge contribution. And that would effectively lead to a contribution. So if you don't account for the larger partial waves, the subsystems which is still in S wave, you will not account for that. So this is necessary.
When you do S wave only, so it's an S wave between the deuteron and the proton, or is it an S wave between the deuteron and the proton and the neutron and the proton and the proton? What is your S wave?
So S wave is always with respect to proton and deuteron.
Okay.
Yeah.
And so now explain that to me. So if I now do, let's say, a P wave, then what changes then?
So basically now you do not look at the deuteron and the proton, but you have two, let's say L1 and L2, two angular momenta, right?
Yeah.
One of them can be still 0 and the other one can be 2.
I see. So now with S wave I have not much choice. Okay.
Exactly.
Okay. Yeah. Okay.
So that's at the
and
low.
there you pick up some attraction which you otherwise don't see. Is that what you're telling me?
Exactly. So you would not see in the two-body cases the S wave is the dominant one, and the proton, if I remember it correctly, it's up to like 2 to 3% effect if you include P and D waves.
Okay.
D wave is almost negligible in the proton-proton correlation function. But here it becomes necessary because you have now subsystems which can still be in S wave.
Okay.
And that would give you additional contribution.
Is this higher partial wave contribution only coming from the interaction when you have three-body interaction?
Sorry, no.
What about, do you have to include
Okay, I got
higher
it.
partial wave without three-body?
No, this is not.
This is only three-body.
Yeah, the three-body effect at this level, again, for the source size which we have right now, it's up to 3% only. It is, I mean, it's all mostly coming in the S wave, but it's only 3% in the entire measurement, like including all the D waves up to D, let's say L equal to J equal to 5 half. So the contribution from three-body is not really significant, and that's what I wanted to show here in the plot over here. So you have like up to 2% for this source size, like 1.4 for me. That's close to the measurement we have now. And this has nothing to do with the source. So we have fixed partial waves up to D wave, and then we change only the potential. In one case we have 1 and 9, in the other case we have just two-body. And the effect is 2% for source size around 1.45. All right. Any questions?
Question on that? Rod?
Who has a question?
Rod, do you want to ask a question?
Yeah, I have several questions, but the one that I put on the chat was in these plots. Can you point us to where the deuteron breakup threshold would be?
Oh yes, yeah. So the deuteron breakup threshold starts at 50 MeV. So the complex
50
imaginary part of the space so imaginary part of the scattering in the scattering phase angle, you can see that it start to increase at 50 MeV around, and that's where you have a little bit of deviation which you would not see in the calculation. But if you see in the second bin over here, we can the measurement is 40 MeV, so you cannot see it, but the effect is very minor. But this is already included in the calculation.
Okay.
Yeah.
So okay, make sure I understand the answer to my question. The part 1 is 50 MeV.
Yeah, around 50 MeV.
And my follow-up was going to be, does this matter? But you're saying it doesn't really matter.
No, it doesn't.
Why doesn't it?
I mean, okay, it should matter in a sense, but if you look at the bin width of the measurement here, it's a 40 MeV. So in order to have any inelastic effect in the measurement, you need measurement precise enough that you see a jump in the correlation function, which you do not because you have here. So in a sense, it does not. In the calculation, there is a slight deviation, but also due to the systematics of the fit, it is kind of smeared out. So it's effect, but it's not significant at the moment.
So you are doing a fit here, right? This is not. It's not a fit. It's not a fit. So we account for the systematics on the fit coming from the systematic of the measurement. That's why it's a width, because you have also the source size. Let me get back to the
the value which is about like, here. So the value is about 1.43 Fermi, and then you have additional uncertainties coming on the source, right? And that also gives you a little bit of width on the overall calculation. From the theory itself, there is no uncertainty on the calculator. So the only uncertainty that we see in the theory is due to the cutoff on the pi-less effective field theory, and also, so there you have some sort of width in the curve, and that's coming from the theory. In the phenomenological potentials, there is no uncertainty coming from the theory. There is a slight deviation. I actually might go even back to there is a purely theory curve I could show you in the backup somewhere here. Right. So right here. So you can see here there is a slight deviation, which, I mean, in a sense you can't see it, but that's where the inelastic process of deuteron breakup starts.
Okay.
It's just the black curve.
All right.
Mm-hmm.
So
right.
Why only stop at the? I'm sorry.
Sorry.
So why only stop at the D wave? I mean, because it explains the data, or if you add more than?
Yeah, no. After that, because when you go to the D wave, at that moment you already have this role of the S wave, like subsystem being in S wave rules out. If you want to go to the higher, in a sense, you don't look at the D wave, but you just wanted to illustrate. You look at the total angular momentum, which is J, and J 7.5 minus is already sufficient enough, because at that moment the subsystem will be like the effect will be less than 1%, and at this moment we don't see it. So it's less than 1% error uncertainty if it has to come from the inclusion of higher order partial waves. Yeah. So I talked about hadron-deuteron correlation function, but there is another way in femtoscopy where we can directly look at the three-particle triplets. And now this is actually a revolutionary step, because you have now not only in the traditional scattering experiments, there was a problem that you cannot really put a constraint on the kinematics of the 3-to-3 scattering. But here you can do it, because the only thing that you have to really do is select the triplet of a particle from the collision and then study the interaction. So the analogy is really simple. Again, you look at the triplet of the particle with the given hypermomentum, Q3, which is nothing but a quadratic sum of the relative momenta of the particle pairs within the triplet. So you just look at the triplet in the same event where they can interact, and then divide by the number of triplets where you pick up the particles coming from different events just to account for the phase space. So this is, in a sense, a measurement definition of, let's say, the correlation function for the triplet particle, and Alice has performed measurement in previous years for proton, 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 and proton, proton, lambda triplets. So on the left-hand side here, I show you here first the proton, proton, proton case shown in the green data points. For large Q3, again, it's a flat, which means that there's no interaction, but in the smaller Q3, there's increase, and then they just drop. Now, comparing this calculation only with the calculation, comparing the measurement with calculations, considering only two-body interactions. So you basically look at the proton-proton correlation function, project the part of the correlation function on the Q3 of the triplet. And what we see that in more or less in the large momentum, it agrees with the data, but at short distances where the role of the Pauli blocking comes into picture cannot be accounted in the two-body case. So there's an effect beyond two-body. Similarly, if you look at on the right-hand side measurement, the proton-proton lambda case, there is a flat behavior at large Q3, but in the smaller Q3, attractive interaction in the system brings the correlation function above unity. And now comparing with the only two-body case, which is shown here in the gray band, we can see that there is an effect beyond two-body, because the two-body alone cannot describe the measurement. And to study in detail, now in Munich group, Laura Sachnitte and Raffaele Del Grande, they have performed a measurement, calculation in collaboration with the INF and PISA people to come up with the definition of the correlation function. Again, you have a single particle sources over here in the calculation, and then you have a three-body wave function as a function of Q3 and the hypermode distance, which we call hyperradius for the system. So the wave function now can be computed again using hyperspherical harmonics for the three-particle system, and this is unbound system, so you can really do the scattering state calculations using R1 V18 potential and then compute the correlation function for different single particle source sizes. And as we can see that the calculations now qualitatively describe the data, but of course this is a preliminary calculation, does not have higher order partial waves included in. But what we see that indeed the Pauli blocking at smaller q, which brings the correlation function down, and it was not possible in the case of two-body gray curve that we used to show. So this already, from both the measurement and from the calculation, there's a way, we have a step forward in the understanding of the three-body systems, not only just the bound system of deuteron and hadron, but also unbound system of three hadrons. And
but the 2, 3 goes to 0. Why the correlation function doesn't go below 1? Because you have a poly principle and you also have cumulant possible. How could they still stay above 1? That's actually what's going on here.
In a sense, yeah, I would agree with you, but it does not go because of the, mainly because, in the calculation, at the moment, the Coulomb treatment is not done properly. So we have like just two-body effective Coulomb, and then the Pauli blocking is only coming from the, the antisymmetrization of the wave function, which gives like more or less at this moment, you would say that in calculation, there is no, we don't know any effect beyond, but in a sense, it should go below 1 because you don't have the pairs.
Yeah, poly principle should also.
Exactly. Yeah. We don't have the pairs, but in calculation, we don't see this effect. Still under
but it's
investigation.
cut off at 0.1, right? So I don't know how it goes when you go plot to 0.
Yeah.
At 0, the Pauli principle really hits you in the face. Right?
Yes,
Yeah.
but I don't think they go down. Otherwise, they will.
No, this part again needs to be further.
Now, another question is about the 200 MeV.
Yeah.
Oh, this is 200 MeV. Sorry,
Yeah, it's in the GeV, so yeah, 200 MeV. Yeah.
I thought it was like a proton collection, so 25.
No, it's in the GeV. Sorry, I should have mentioned the dimensions. Yes. So the calculation is in place. Works. In a preliminary case, we can see that qualitatively it's provided description. There's a very step forwards in the, you can really also plug in the three-body contributions and then study the correlation function.
You really talk like a series. You say this works. Comparing to data.
Well, it's like in the first time the 3-to-3 scattering process calculation, right? So we need to really look forward towards the positive directions and appreciate that. So yeah, indeed, it works. It qualitatively provides a description. Of course, there is a fine-tuning of the calculation. And this is
sigma, it seems to be fine for me.
Yeah, also like, the error bars are rather large here. So I would really take it as a good description. Of course, here there is a deviation, and that's where I wanted to mention that in this calculation, we do not have higher order partial waves included, like the strong interaction. So this, if you include, because in this region also the higher order partial wave will hit in the calculation, and that will bring the correlation function. The preliminary calculation already have it. I don't have the updated plot here, and we didn't, but this is already there.
To me, the data really looks like Fermions, including Coulomb interaction. You see the peak at 200.
Over here?
Then go down.
This one over here? Yeah. So it's like, it's similar to the
quantitative is systematic.
Mm-hmm.
The calculation is not fit.
I'm so shocked by the scale. 200 MeV, typically you have the proton that goes up to 100.
Yeah.
So why is that all shifted to such high momentum?
So the reason is, in this kind of measurements, you need to select a 3 particle, right? And there are rare events that you will have a triplet. So the only reason is we don't have statistics. Otherwise, we would really have.
No, I'm thinking about the calculation. Why don't I see the attraction at such a large relative momentum? Why don't I, in the proton, I don't remember, what is it, 50 MeV, 30 MeV?
20 to 25 MeV. So there's a peak in the 25.
Yes, right.
Yeah.
So now I take 3/2 of this by the principle of insufficient. No, 3 times instead of 75 MeV. I have 3 pairs, right?
Yeah.
So why am I at 200 now?
So in the principle, I agree with you. It should go really like bump over here and then come back.
Yeah.
But it shouldn't, because you have now 3 particles in game, and they can have a polyblaking already starting at over around like in the range of 30 to 50 MeVs. What we see here is like, again, it's the same rate. So you have relative momentum between the particle pairs, right? So one of them can be really in a large momentum, and the other one is really close to each other. And that will also like, bring here smearing in the correlation with the signals. That will bring also like towards larger. It has to really shift towards large one. Right?
How are these C's normalized? Can you remind me?
So there again, the normalization is we take unity means there is no interaction between particles. And there the normalization is really complicated because we have now 3 particles, right? So the normalization can be really like around 1 GeV or somewhere over here. And we go to like.
Is there some rule?
Yeah, actually there is one. So the measurement will be again performed in run three, and then we will do the measurement up to, let's say, 1 GeV or even large, and then there will be a like matching.
The summer rule correlates high Q with low Q. Right? You got it's just systematically you're missing the measurement.
Yes.
At very high Q by many sigma.
Right.
I mean, the error bars grow, sure, and there's
over here, right?
make
So
excuses, but in high sigma, in high Q, it doesn't work at all.
Yeah, it doesn't work, and there are two reasons. The first one is inclusion of higher order partial waves.
Sorry?
Inclusion of higher order partial waves. So we don't have any P and D waves like we had in PD correlation function. We need to include here, and the second one is properly normalize the theory and the experiment in the large range where we do not expect interaction. This is not done yet. So it's just like putting a theory curve close to the data, where we expect that they should go
so
large.
Do you have some freedom to move the theory curve up and down?
Yes, of course. Two reasons I mentioned already. Inclusion of higher order partial waves. This is one of the reasons, and the second one is the baseline that we don't have it here, like I have in the PD case. So the baseline here indicates that the proton and deuteron can come from a material kickout, right? And they could also play, but they will not be playing a part in the final state interaction, but at large case target definitely can. And so we need to really constrain this baseline, which will be done for also Q3 measurement.
So just we understand. So for the three body, I mean, there in principle, if you had a perfect detector without any dirt, and you go to large whatever Q squared, this correlation function should be 1.
Exactly. That's
right.
Why.
And the fact that you have normalization problems is that you have protons coming from your material, or what makes this normalization so difficult?
So the first thing is you have different freedom. So you
definition.
can. So the normalization is given such that I can't go back to the right. So okay, I'm sorry. Here. So you see this is a free constant over here, right?
So what's this n? This
exactly.
N?
Exactly. So the n is chosen such that it becomes 1. So you have a two distributions.
It's an experimental fudge factor.
Yeah. So this should be taken into account when you fit the data. You need to let this parameter as free because you don't know the normalization constant.
Why don't I know? Why, if I had a perfect detector, n should be 1.
Exactly.
And so the fact that n is not 1 is that you get fake pairs from detector effects, or I mean, you must have some way of understanding n not being 1. What's the reason for n not being 1 in reality when you have a not perfect detector?
So there are two reasons. Not only just the detector, but it's also the physics. So in the physics where you can have a weak decay, for example. Yes. So you have particles coming from a weak decay, which would not really participate in a strong interaction.
Yes.
But that could really affect your underlying baseline of the correlation function class. This needs to be taken into account.
Yeah.
So maybe we go back to that Q3 plot we were just discussing. So I don't know, but it seems to me difficult to really in the there we go. Yeah. Theory calculation, the model, all the weak decays and all the detector stuff and so on.
Yeah.
So let me ask again, do you have freedom to, given these qualifications, do you have freedom to normalize the theory curve and the data to 1 at high Q?
Yes.
And if so, why have you done that here?
So the only thing is now the measurement was only performed up to 800 MeV.
That's not high enough to be.
Exactly. So we need a large tail of the data where we expect that there won't be any final state interaction, and from there we can constrain. So we will have some sort of constraint from the large long range correlation function.
So the calculations don't have any such. Right?
Yeah. No, the calculations have no freedom except for.
So why is it below unity? In my eyes, right?
Yeah, I agree with you. Of course, there's like in the high precise data over here, you can see there's a significant deviation.
No, talking about the color curves.
This is because mainly we don't have the higher order partial waves included in.
Yeah, okay, you already said that too. So the experiment you haven't got the high enough Q.
Yeah, exactly.
And the theory you don't have enough partial waves.
The work is already in progress, so we'll be having soon, better inclusion of higher. Yeah, indeed. Now, so we have this proton case which is done, and the the calculation is already in progress in parallel with the proton lambda, which will be then again having similar.
Coming back to the agreement of data and theory, give these caveats. That if all we have is what we have in the plot, the theory isn't going anywhere, so I can just put that to 1.
Yeah.
Let's just do that, and so it already goes up much closer to the data, and then you're just missing a few points.
Exactly.
So the answer no. It's actually better than it looks on the plot.
Right. All right. So now we have so the progress normally is from the measurement, from the theory as well. So there's progress from both sides, and we are actually looking into. I think there is a comment from our question in the chat box. I don't know if I checked. All right. Okay, this was already done. Sorry. So there is a progress from both sides. We look forward to run 3 and run 4, where we will be putting the precise data on the plot, and then we have a comparison. So this was, I was talking about mainly the 3-body cases in run 2, and now talking about run 3 already. The first thing that we need to do is perform the source measurement again, because you have now different luminosity, and then there's a bunch of particles are produced again with different interaction rate. So we need to do the source studies, and this has already been done for the preliminary data from run 3 in 2022. So the estimate on the pair statistics here is of 2 orders of magnitude, and with such a large statistics, now we can perform a correlation function not only just in the transverse mass windows that I showed you before, but also in different multiplicities. So you can choose the particles in different multiplicity ranges, and then you can perform a fit, extract the source, and then look at the empty scaling. And this we have done, and here you see is now not just one scaling, but several scalings for different multiplicity. This really opens door to many measurements, hadron-hadron interaction or 3-hadron interactions for different multiplicity as well. And this is already a really good work in progress, and it's ongoing effort in run 3.
Why do we expect a different scaling?
Because you have now the centrality which is changes, right? So you have you can have more particles produced, you can have smaller, less particles are produced, and if many particles are produced, the distances will be smaller, and that's why you see this shift in the scaling as well. And that's being captured by the correlation function performed in different centralities. So this is one example from one of the fit here. You can do it for several different, and then extract the empty scaling. Cool. So this was one of the way. The other way to study interaction is, I really want to go into the detail, and this was if you look at the production mechanism of light nuclei, they also provide you in a way to study, provide a way to study interaction. For example, now a deuteron can form from a proton and neutron coming out of a collision fireball, let's say. And on the way then they fly out, they can form a deuteron. And if you study the deuteron production, you can go to the interaction. So classically, this has been, previously people have already been looking at it. Deuterons are light nuclei, also the other light nuclei where the binding energy is of the order of 2 to 3 MeVs, while the collision experiments, if you look at the temperature, it's of the order of 100 MeVs. So it's like snowflake in a fire, and snowflake is popping out of a fire, which is really difficult, difficult to accept it. But this is happening, and it's really important to now understand not only just the interaction, production mechanism as well. So here there are 2 different ways to try to understand this process, or let's say efforts to really go into the detail. The first one is to look at the statistical hybridization model, and there the idea is you just populate the available phase space in the collision, and you predict the yield, and that's it. So you have the yield of the deuteron, but you don't know how the deuterons are formed at the first place. The second way is to look into the coalescence way. So you have nucleons produced, and then on the way they fly out, they can actually interact, or some random kick of ion can really lead to a formation of light nuclei, such as deuteron. So this is more like quantum mechanical process. So it also provides some microscopic details of deuteron nuclei formation. Right. So this is where I also focused during my PhD to understand whether we can really use coalescence as a final state interaction to predict the deuteron light nuclei production, and then study the role of proton nucleon interaction. So I don't want to go into the detail of the formula here, but what I want to point out is the 3 terms over here. The first one is Wigner density, and this is where the interaction between proton and neutron comes into play via the neutron wave function. The second one is a source from which the particles are emitted, And this is, again, it can be constrained from the femtoscopy, as we have shown. And the third one is just momentum spectra of the nucleons. And this can be taken from either some simulations, for example, EPOS and PTIA that we have used in our studies. So we have ingredients in HAD, and what we need to feed into the, the event generator program is the probability distribution, which is dependent on the source size and the relative momentum of the nucleon. And this is just the first two terms integrated over the phase space. Now, we can do that for the deuterons. And so here I show you the measurement of the deuteron yield as a function of transverse momentum in high multiplicity proton-proton collision. So we can see that there is a distribution of the data points from the proton-proton collision. Now comparison using event generators, two different event generators. The first one here I want to focus on is the solid one, which is EPOS, for three different choice of interactions you can use. So the green one is Hulton wave function, where again the Hulton wave function classically in the past people have been using it, and there the thing that misses out is the core nuclear interaction because you don't have a repulsive part. The second one here is the blue one, which argon V18 potential has been used for the femtoscopy analysis before. Nicely describe the data. And the third one is rather a harmonic oscillator approach. So you say that the deuteron is a harmonic oscillator and just predict the bound state wave function using a Gaussian distribution. And it actually differs a lot. So what we see here, the production mechanism can also tell you a lot about the nuclear interaction. And in future, we are looking at not only just the deuteron, but also helium-3. The calculation is already under progress, and triton as well. This will give a way to study interaction in three-hadron system from the coalescence perspective. So with this, I come to the summary. I think I was talking already a lot. I won't really repeat my summary, but let's go to the outlook. So we have a bunch of like run 3 and run 4 coming up. So we'll have lots of statistics available in the market. We can use that and then perform not only the PD, but Lambda D, Lambda sub CD, and also the three-hadron systems from, for example, proton, 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 and proton, proton, Lambda, and then perform studies and pin down the three-body forces in such systems. And that will be not only useful for nuclear physics, but also for astrophysics, for example, neutron stars, where we will be. So with this, I would like to thank you very much.
Any more questions or comments?
Yeah, one to your coalescence business. You said that the one interaction didn't have enough of a hardcore repulsion. And I mean, so when you do effective field theories, does that work? What have you
It's a very nice question. Actually, yes, we do. So we did the kernel effective field theory at N5 very precise there. And this actually goes over the argon V18 potential. Exactly similar. I think I might have somewhere.
To the argon V18 potential. Okay.
So I think I might have somewhere plot, but if I have, I didn't put it.
Well, okay, I'll take your word for it.
Yeah.
Okay, all right.
That's really nice actually, because both the argon V18 potential and this finalist effective field theory, the deuteron wave function, if you look at it, it's very close to it, except for very small distances where I think the final state interaction is still relevant, but in such business where you have
you don't have enough resolution.
Exactly.
Okay.
Yeah.
I don't understand. This is consistent. What do we do?
Oh, because the effective guys, they just put a delta function essentially in the middle. They don't really put a beautiful potential to the finite hardcore range, but that's probably for this resolution simple enough.
I have a question. So for Laboche-Smirnitsky approach, in their paper, they said in order to apply that formalism, they require the smooth assumption. The source has to be smooth, otherwise will disturb the final state interactions. Right? There are two terms. Right? The source term, the wave function term. The source term is the collision dynamics. Wave function is the final state interaction. You think in TP collisions, you satisfy this condition?
Even you want to say that the LHC formalism, right? Hello, but the smoothness approximation is throughout the femtoscopy business, not only just for the one. It's also like if you look at the Coulomb-Pratt formula here, you need to, all the three standard assumptions are there in this calculation here.
How do we understand TP collision so dynamic?
Yeah.
It gives you smooth source.
No, but that's what like we wanted to, so we assume in the beginning that we don't have a smooth source, but we use a Gaussian distribution with such business, and it turns out that we have a constraint, right?
This constraint, I also
but the second point here is, if you look at the triplet correlation functions, so for example, in the PP collision,
much more difficult cases.
No, I wanted to make a point here, is that you don't see many triplet over here in this small relative moment, which means that in effect, you can say that, okay, the volume is a small particles are being produced, so that many particles are nearby. But from here in the measurement, we can see that the triplets are not there, like not many. Of course, there will be effect due to the subleading orders, the particles which are close in the phase space for the correlation, but at the moment we don't see it.
If triplets are there, what do we expect?
If the triplets are here in this range, we would also say that these triplets, so basically...
in terms of measurement, what do we expect? In terms of measurement.
Here,
yeah.
I mean, in the proton-proton case, you can't expect because there's power blocking. No, they should be. My argument is not about they should be or not. It's the in proton-proton collision, high multiplicity measurement, we don't see these triplets. That's the argument. So since we don't see it, we would also expect that the proton-proton correlation function, the neighboring proton would probably not exist because in such small relative momenta, the triplets are also not there. It's just like putting a kinematic constraint on the measurement. This is the argument goes that way.
No, go ahead.
Yeah. I wanted to maybe go back to my original question. I'm trying to understand like the form, like how formally sound these ideas are. Like, you know, when I asked about the deuteron breakup, you said it wasn't a problem, but you didn't have to change slides. But okay. You said it wasn't a problem there. But then you go into really high energies in the last plot that you had, right? There's going to be many open thresholds at that point.
Yeah.
It sounded like your explanation for that was more empirical rather than there's any, you know, there's no formal limitations. Let's put it that way. Like, you know, what would be a smoking gun of this not working correctly? Like, or what principles are you violating? Like, it would work.
So you want to say, okay, let me just try to understand what you wanted to ask. So first thing is, if there has to be a deuteron breakup which is anticipated and it should be there in the measurement, right? I mean, because you have energies which are large enough. And from the calculations, we do see the imaginary part of the phase shift which increases already starting at 50 MeV in the K star, and then it goes on increasing a bit. So this is sort of like, you know, from the calculation, from the measurement, if there has to be any deuteron breakup, which would mean that you tend to measure less deuteron-proton pairs than what you would anticipate, because, you know, you lose particle pairs over here around 50 MeV, and that should open up, you know, some sort of an elastic channel, and that would give a jump in the measurement. At the moment, we don't see it, but I definitely agree with you. If there has to be, which is there, deuteron breakup, it will be observed here in the measurement, and it will be there. The calculations already take into account the deuteron breakup by looking at the inelastic cross-section measurements. So they just put the calculation. Michele has already done this calculation, assuming that the deuteron breakup takes place in the measurement. Yeah. I think I tried to answer your question whether it is sufficient enough or not.
Yeah, I guess. I guess. Maybe if I zoom out, right, is the idea, right, is that these correlation functions, they allow you to describe, you know, they allow you to perhaps get access to, you know, these pseudo two-body states, or, you know, possibly three-body states, and you're gonna have to have some parameterization of their interactions that then gets fed into the wave functions. You're gonna tune those parameters, and this class of observable, you know, you can do this procedure independently of whether you're above some breakup threshold, because it's not just a deuteron, right? Then you're gonna have like pion production threshold and pion production, right? I mean, you were like scanning really high energies, right?
Right.
So the conceptual, you know, procedure is independent of the kinematic region. It's just whether you have a a theoretically robust parameterization
Yeah,
or not is an open question.
No, I got it. Yeah. So from the method wise, there is no issue and there is no obligation that you won't see such effects. And indeed, we see. For example, if you look at the proton lambda correlation function, there is a clasp-like structure. This comes out because of, inelastic channel opens up over there. Sure. So this is essentially becoming, some sort of inelastic process being included in the, this would be popping up in the measurement, and that we see in the correlation function. This is completely independent of the calculation, or there is no empirical assumption over there. Yeah.
Right.
Does that answer now?
Yeah, I think so. I mean, I guess the point is that at the end of the day, the systematics are going to rely on what functional form you use to describe the data, right? And tease out
exactly the modeling is
three-body, right? Yeah. Okay.
No, there's a problem that, for example, now again, pinning down the three-body contribution will be really difficult. It's not so easy, and I mean, there will be several arguments about that. And the modeling needs to be done properly. At the moment, what we have is it accounts for the inelastic processes, and there is different stuff. For example, different system we measure, lambda deuteron or something else, and there probably. I mean, interestingly, I can tell you already one thing that comes into my mind. So I'm doing already analysis of pion deuteron. Imagine now a pion and a deuteron in the phase space. So the pion and nucleon can come from a delta decay, right? So that you would directly see in the measurement. There's a bump-like structure in the correlation function which you would not anticipate if you do the model calculation. And this solely comes from the delta decays, and we have seen it, and probably in the next few months the paper or at least preliminary plot will be out. So this is indeed interesting, and we have seen in several different systems. So it's up to the measurement, and then modeling is different.
Okay.
Well, I have a question. Maybe I've just come across this. Do you know whether there is any measurement of lambda correlation in any system?
Yes, we have in Alice. Lambda. We have also put like a constraint on the.
You have it, but not published yet.
It's published result.
Published.
Yeah.
Oh.
It's published in 2019.
Is this in PP or in
PP collision?
It's repulsive, right?
Yes, because of the first power blocking nightly anticipating, and then there is also in star. I think
Star also.
Okay. Yeah. Maybe I can find out the reference.
Yeah, I can also go put. I think I will already be there somewhere. I can put. So
we could leave the slides with us. We have the slides, and would be very.
Over here, you could go to this publication over here, and this is the lambda.
Oh.
We could also take into account the baryon and anti-baryon, proton lambda, proton anti-proton, lambda anti-lambda.
But this is only in PP, right?
Yeah, in PP, all of these measurements. We choose PP collisions mainly because we have smaller distances here, right? I mean, if you look at the lead collision, the distances will be large enough that you don't see the effect of the three-body forces at that. Also, so we need to.
It would be nice to look at also in AA because you want to look at the interaction range.
For example, the PD, we are already doing the measurement of proton-neutron correlation function in lead collisions at semi-central, central, and then. So
maybe can you get the slides?
Yes.
I sent it to Nu already. So
all right.
Okay. Thank you.
Okay. So let's thank Dr. Disconnect.
Thank you very much for joining.